So that was an example of a weighted residual method. So let's talk a little bit more about the types of weighted residual methods. So depending on the choice of del ui, like so I'll just say also, I chose the approximating functions, the phis, and the weights, del ui, both sort of without explaining why I chose what I chose, okay? That's not a very good way to tackle problems, right? So what we're headed after is a systematic way to choose both of those, okay? And so that's where we're going. We're not there yet. All right. If we choose del ui such that if the, I called it an arbitrary function. In a lot of times in the mathematics literature, you'll see it called a test function, okay? So if we choose the test function to be equal to the approximating function that we chose, those approximating functions, the phis, are also known as basis functions, right? So if we choose the test function to be equal to the basis functions, then we have what is called a Galerkin method. If we choose something else, so the del ui to be not equal to the basis functions, we have what's called a Petrov Galerkin method. If we chose the del ui to be equal to the right-hand side of the equation, where we've replaced the u with phi, we have what's called a least squares method. It's called a least squares method because basically you have what's in the integrand will be squared, right? So you have del ui times something. If you choose del ui to be that something, then you have that something squared, right? If you choose del ui to be equal to a Dirac delta function, then you have what is known as a collocation method, where this so a Dirac delta function has the property that it's equal to 0 when x is not equal to xi, and it's equal to 1 when x is equal to xi. So I think you might have heard me say in a previous class that basically all the common discretization techniques, finite differences, finite volumes, can all be cast in the formalism of finite elements, right? And so the way you get finite differences, a finite difference formulation, because in finite difference formulation we compute the derivatives at points, right? That we just have nodes, right? And so basically you can choose your test function, or your del UI, your test function, to be a Dirac delta function located at the nodes, and then you get, because of this property, basically it's 0 everywhere else and 1 at the nodes. And that's the first step for recovering a finite difference method from the finite element method. So only least squared methods result in a symmetric coefficient matrix. Now, I didn't write down what the coefficient matrix was for the problem we solved, but had I written it down, or I'll write it down now, you'll see that it was this. So obviously this is not symmetric. Why do I care? Why do I care if it's symmetric or not? Solver, yeah. So here we didn't need to use a computer to solve this, right? But if we had had 1,000,000 unknowns instead of 2, we'd have to use a computer. And we prefer, it's not the end of the world if it's not. We have solvers that can solve non-symmetric problems, but our best solvers are, or if you have a symmetric problem, one of the best solvers you can use is a conjugate gradient method. But conjugate gradient method only converges if your matrix is SPD, like symmetric positive definite, right? So we prefer to have symmetric coefficient matrices for those reasons. Also, kind of a secondary reason is it's less important these days. We have plenty of memory on our computers, but if you have a symmetric matrix, you only have to store half of it, right? Just one half of it. So, yeah. So we prefer, if we could, to come up with a scheme that will give us a symmetric matrix. And that scheme, or a scheme that will do that, is called